Alright, this is video 2 for the simple harmonic unit notes. Now for this one, what's kind of neat about simple harmonic motion is that we can represent this with either a sine or a cosine graph. Now when you're in math, you probably learned that sine and cosine are basically the same features for the graph. They just start out of phase with each other. So imagine, for instance, that I have a mass spring system oscillating up and down. And then I put some sort of marker on it so that it moves up and down and draws a line. And then I take some paper and I move the paper out from underneath of it. Envision how this would work. So as the spring system oscillates up and down and as the paper is pulled out from underneath of it, we can get that classic sine or cosine looking graph. Or if I have a pendulum moving back and forth, put a pencil on it, and then pull some paper out from underneath of it, notice how I get the same exact feature. So oscillatory motion, whether it's simple harmonic or mass spring, we can represent that with either sine or cosine graph. So what that means is we have some things we can start to look at. First off, we can have amplitude. How far away from the equilibrium position. So as this thing oscillates, this right here would be your equilibrium position, and then this would be like your, I think before we called it X max. We also have wavelength. Now we represent wavelength with a Greek letter called lambda. We also have period. Period would be the amount of time it takes to go from one wavelength, or the amount of time it takes for one wavelength to pass by. So, also look how as this thing oscillates up and down, that would draw out one complete wavelength, and that's the period. So notice how the period and wavelength go together. And then obviously we can get frequency just by taking 1 divided by the period. So when it comes to this type of graph, here is the model that represents it. I'm going to put a little tiny alpha symbol beside that omega. So it equals the amplitude, which we were calling X max, times sine. Before we were using cosine, but honestly, they're almost interchangeable. We got angular frequency times time plus k times x. Now that k may be a little new. So let's go through what these are. So y, this is going to be the amplitude at a certain moment in time. Capital A is the maximum amplitude. Omega, I'm going to put a little alpha sign beside this because this is our angular frequency. Remember that it's 2 pi times f. That's what that is. T is time, but I want you to think about it as a moment in time. All right, now for something new. K is called the wave number. What K equals is 2 pi divided by wavelength. And what it is it's like a spatial frequency. It's the cycles per unit distance. Frequency, F, is kind of like the cycles per unit time. How many oscillations happen in a second. It's kind of like angular frequency or frequency. Spatial frequency is how many cycles per unit distance. We've got X and this is basically the position. It's a position in a moment of time. Finally, in this model right here, positive means that the wave is moving to the left. If there's a negative here, it means the wave is moving to the right. Different textbooks will have different notations for that, so don't be surprised if you see the opposite, where negative means to the left and positive means to the right. I'm just going with this convention, but it just depends on what textbook you're reading. All right, so let's look at an example here. So here we have a formula that's describing a sine wave. So here's some things we can pull from this. First thing I can say is that the maximum amplitude is 60 centimeters. The next thing, I know that angular frequency is 2 pi times f. So what that means then is I got 4 equals 2 pi times frequency. So that means that the frequency equals 2 divided by pi, and the units for frequency are hertz. All right, moving right along, that means I know the period, because period is 1 divided by the frequency. So the period is pi over 2 seconds. The wave number, it is 2 pi divided by the wavelength. So what that means is I've got 10 equals 2 pi over the wavelength. So that means that the wavelength equals pi over 5 meters. The velocity of the wave equals wavelength divided by period. So that means that I have pi over 5 meters divided by pi over 2 seconds, and that equals 2/5 meters per second. Finally, I know that the wave is moving to the right. So out of that one model right there, we can pull a lot of information, a lot of useful information. Energy. Okay, so a system with internal structures can have internal energy. And the systems, we have a mass spring system, and then we have the bob earth system and the pendulum. Changes in a system's internal structure can result in changes in internal energy. So what the statement basically is telling us is that we can apply conservation of energy to help us understand how the system oscillates. So we've seen this type of graph before, where the potential energy is a parabola and so is the kinetic energy, and they're opposites of each other. And when we add them together, we get the maximum kinetic and potential. It gives us the mechanical energy. So basically, depending upon the system, we can find its kinetic energy or its mechanical energy. So for example, if we have something like this, we know its starting potential energy equals 1/2 k delta x squared, and its starting kinetic energy equals 0. So its mechanical energy is just 1/2 k delta x squared. And that stays the same no matter where we look. and we can do some conservation of energy type problems on this. All right, that concludes our simple harmonic motion unit.